Hello everyone, I'm Thomas, and today we have an exciting topic to discuss: calculating delta V for plane change maneuvers using GMAT. In our last video, we went over the basics of using NASA GMAT, but now we're going to be utilizing the Burns resource to perform our first orbital maneuvers. Plane changes are crucial maneuvers performed by spacecraft to alter their orbital inclination, allowing them to reach specific targets or optimize their missions. During this tutorial, we'll cover the fundamentals of plane changes, including the principles behind orbital inclination and how it affects spacecraft trajectories. We'll define our test problem, calculate an analytical solution, and then we'll dive into the GMAT software and perform the maneuver with our analytical solution, then exploring how we can use GMAT and iterative methods to give an estimate for the maneuver. Okay, so let's start with our problem. Let's say we have a circular orbit around the Earth at an altitude of 8,829 kilometers at an inclination of 50 degrees. And we want to perform a plane change maneuver to an equatorial orbit with an inclination of 0 degrees, but maintain our current eccentricity and semi-major axis. In essence, we want to keep everything else the same, but just change our inclination. We need to perform a plane change maneuver. And this is a single burn maneuver, and it must be carried out at the intersection between the initial orbital plane and the desired orbital plane. And typically this means it's carried out at the ascending node of an orbit, because it means we can save the most propellant. So let's start with an analytical solution. We first have to calculate the total delta V required for the plane change, and this is done with this equation. So we have delta V for a simple plane change is equal to 2 times the circular velocity times the sine of the degree of plane change that we are carrying out. So you'll recall that our circular velocity, v circ, is equal to the square root of our gravitational parameter over r. And the gravitational parameter is in kilometers cubed per second squared, and our radius is in kilometers. We know that mu is equal to the gravitational constant times the mass of the central body, and the central body in this case is Earth. So the gravitational parameter for Earth is 398,600 kilometers cubed per second squared. And that gives us our circular velocity of square root of 398,600 over our radius. So our altitude is 8,829, and we need to include the radius of the Earth. So because the center of the inertial reference frame is at the geometrical center of the central body. So that's 8829 plus 6371, which is the radius of the Earth. And that gives us a circular velocity of 5.121 kilometers per second. So we've got our circular velocity, and now we need to figure out our theta. So this theta term is simply going to be the degree of change that we're carrying out. So that's going to be 50 degrees because we're starting with an inclination of 50 degrees and going to an inclination of 0. So let's move over here. So our delta V SBC for a simple plane change maneuver is going to be 2 times 5.121 times the sine of 50/2. And that gives us total delta V of 4.323 kilometers per second. Well, that's all well and good, but what we need to do is break this up into its velocity components. And we can recall that our circular velocity is the same in our initial and final orbit, since circular velocity is proportional only to the gravitational parameter and our radius. So what we need to do is we need to utilize the vector components here. So we can break this up even further by using this equation. Where we take our x component velocity as the velocity of the final orbit times cos theta minus the velocity of the initial orbit, and that's our I component, plus the velocity of our final orbit times sine theta, and that's our j component. And in this case, we need to consider that we're moving down 50 degrees. So the plane changes, we're not increasing our inclination, but we're decreasing our inclination. So in this case, theta is going to be negative. So given that our initial and final velocities are the same, what we end up with is, come over here, delta V SBC is 5.121 cos of negative 50 degrees minus 5.121 and 5.121 sine of negative 50 degrees. And what that gives us is a delta V SBC of minus 1.829 and minus 3.923 in the I and J components in kilometers per second. So now that we have these values, we can try and plug these into GMAT and see what happens to our spacecraft. So let's head over to GMAT now. Okay, so welcome back to GMAT, and now we're going to be testing our analytical solution in the GMAT software to see if our analytical solution is correct, and we can see that with the visualizer. So we're going to start in the resources tab and define the resources that we will need for our mission. So the first thing we're going to do is we're going to rename our default spacecraft to SAT-1, and we're going to double click and open this up, and we have our spacecraft window here. We're going to change our epoch format from this to UTC Gregorian and change our state type to Keplerian. Now our semi-major axis for this is 15,200. Eccentricity is 0. Our inclination is 50 degrees. Our ascending node is going to be positioned at 90 degrees, and that's from the vernal equinox to, and that's the angle from the vernal equinox to the ascending node. And our argument of perigee is going to be 0, and true anomaly is going to be 0. I'm going to click apply and OK. And now what we're going to do is we're going to configure our burns. So in GMAT there are two types of burns. We have impulsive burns and finite burns. The impulsive burn gives you all of your delta V instantaneously, whereas the finite burn gives it you over a period of time. So we're going to select impulsive burn, and we're going to rename this to simple plane change 1. And we're going to double click, and here we have our impulsive burn parameters window. So this is where we're going to put our solution. We're going to leave the coordinate system as it is, but we're going to put our solution here, which was minus 1.829 in the x direction. In the y direction, it was minus 3.923, and the z component was 0. We're going to click apply and OK. And for the output, we're going to select default orbit view. We're going to check that our spacecraft is selected and our celestial object is selected as Earth. We're going to leave the view definition as it is, but I'm going to get rid of the stars so things are a little bit clearer. I'm going to click apply and OK. And now we can start configuring our mission. So in the mission sequence, we need to outline the order of events that are going to take place. So for this particular plane change maneuver, a particular set of things needs to happen in order for the maneuver to take place. So the first thing we have here is our propagate 1, and this is our initial orbit. And this is just going to propagate over a period of time for 12,000 seconds. So we can leave that as it is. But I'm going to insert after and propagate again. And in order for the maneuver to take place, we need to move the spacecraft from its initial orbit to a point in its orbit where the maneuver can take place. And you'll recall that was at the ascending node. So I'm going to call this go to ascending node. I'm going to double click on this, and our stopping conditions are going to be the true anomaly position, and we're going to set the true anomaly position such that it aligns with the ascending node. So our ascending node was at 90 degrees, and our true anomaly is going to be set at 180 degrees. Because the positions of the ascending node is in reference to the vernal equinox of the orbit, and the position of the true anomaly is in reference to the periapse of the orbit. So that's why they're slightly different, but you see that we can test this now. So I'm going to click apply and OK, and I'm going to save this as simple plane change. And we're going to run this and see if it propagates us to the correct position. So if I hit play, you can see that we stop now at the right ascension of the ascending node. So this is the ascending node because if we kept going, we would be moving up the orbit. And we can see that the inclination is set at 50 degrees. So everything looks to be okay. So now we're in a good position to begin our maneuver. So I'm going to close these windows, and I'm going to insert after. I'm going to put maneuver. I'm going to call this simple plane change 1. And when I double click into this, you can see that it already says that we have a burn and the target spacecraft for that burn. So we have SAT1 and our simple plane change 1, which we configured earlier. So we're going to click apply and then OK. So now that the burn's taken place, we need to propagate out of that burn. So we need to put yet another propagate. I need to move that. Insert after the maneuver. And I'm going to rename this to final orbit. Double click on here. Now I could leave this as elapsed seconds. Instead I'm going to put it as elapsed days. And I'm going to set it to 1. And I'm going to override the color so that we can see clearly when it changes into its new orbit. Click apply and then OK. Save, and let's see what we get. So here we can see that if I slow the animation down, we start from our initial orbit and the plane change is performed at the ascending node, and you can see that the values which we calculated were correct because we were able to achieve a orbit that is in line coplanar to the equatorial plane, which is this blue grid here. So now that we know our solution is correct, what can we do if we know our target inclination and we know and we just want to perform the plane change maneuver, but we don't necessarily know what the delta V is going to be. And this is kind of where GMAT shines. It's underpinned by solvers, and it's not intended for you to know the delta V's and be able to calculate every delta V analytically, because that, as the mission gets more complex, something like that just isn't feasible, and the equations become very difficult to solve. So now what we're going to do is we're going to try and achieve the same outcome, but using an iterative method, and see how close we can get in terms of an estimate for the delta V required for this maneuver. Okay, so I'm going to close these windows now, and we can leave this as simple plane change 1. But what we need to do now is head back to the resources tab, and we need to add a solver. So what we're going to do is we're going to add a boundary value solver, and this is called a differential corrector. And you can see here that it uses an algorithm or a numerical method called Newton-Raphson to converge upon a solution. And what you need in kind of most of these numerical methods is you always need to outline your boundary conditions and your initial conditions. So that's kind of configured within the resources tab. But the more information you give it, the more likely it is to converge upon the solution. So I'm going to leave the max iterations as 25, but we can adjust this as required. Remember, we said that GMAT is a batch execution model. So what we do is we run it, we adjust the script, and we keep running it until we converge upon a solution. So I'm going to click OK here, and we're going to leave this as the default differential corrector. So now I'm going to head over to the mission and make some adjustments here to our mission sequence. So I'm going to insert after, and what I'm going to do is I'm going to set a target, and this target is going to be called SBC1, and I'm going to delete our previous maneuver, and instead now I'm going to work within this SBC1 group. So the target just defines the point in the sequence where we're trying to converge upon a solution. So we set a target parameter, and within this kind of tree is everything that is all of the solution and all the problem solving that goes towards converging upon that parameter and the desired parameter that we want. So typically what happens within these target features and this target function is we need to outline a vary command. So what's going to happen here is we're going to click insert after. No, we're going to put append, and we're going to come to vary. So what we need to do is we need to vary the delta v's until we converge upon the desired orbit. So this one's going to be called vary underscore vx, and that's our velocity in the x direction. And if we double click on this, you can see it's selected our solver, and what we need to do is ensure that it's selected the correct part of our impulsive burn. So we can choose a variety of object types here. We're going to select impulsive burn, and you'll recall that element 1 in the impulsive burn tab was the velocity in the x direction. So that's why I click that, and I'm going to ensure that's the selected value and click OK. And here's our initial value, which is 0.5, our perturbation, our lowest value, and our upper value, and the max step. So we can set really large ranges of potential solutions here, but it may take longer to converge upon a solution. But we know roughly that it's going to be a negative value, so we need to adjust our negative value. So I'm going to adjust it to negative 3.14159, and we're going to leave the max step as 2, and we're going to click apply and OK. What I'm going to do now is I'm going to insert after, and I'm going to put vary vy. Click OK. And I'm going to open this up. Now it's selected element 1, and we need to change that now to element 2. And likewise, I'm going to select this as, this time, negative 5, because we know roughly that the solution was minus 3.9. So we need to ensure that the range of data which it's testing is going to be between those two values. So I'm going to click apply and OK. And now I'm going to insert after and put vary vz. And I'm going to leave this just as it is, and select element 3. Click apply and OK. And the reason why I put vary vz there is because although we know that there's no component in the z direction, we still need to give GMAT the flexibility. In GMAT, it's not going to be able to give us exact values. For example, even if it is 0 analytically, since GMAT uses numerical methods, it will never truly arrive at 0. It will be very, very close to 0, but it won't be exact, which is why it's an estimate. So now what we're going to do is we need to insert the maneuver. So we've chosen all these vary commands. So GMAT will choose the vary. It will start at its initial value, and for all of these elements and these components of delta V. And then it'll perform the maneuver, and we're going to call this a simple plane change 1. And we can leave this as SPC1, SAT1, click apply and OK. And now what we need to do is define how we're going to describe our desired orbit, and how does GMAT know when to stop. So what we're going to put is the achieve function. And the achieve function, we need to describe the parameters in which we can tell the function to stop. So for this, it's going to be the inclination. And I'm going to double click on this and set it as satellite 1 Earth, and currently set as the R magnitude. Instead, what we're going to do is inclination. And click OK. I'm going to set this value to very close to 0. If we remember, it's a numerical method solver, it's never going to truly arrive at 0. So I could either set it as 0 with a very high tolerance, like a tolerance of 0.2 or 0.4. And that means that we can give GMAT a little bit of leeway in terms of converging upon a solution. And it also is quite useful for us because we can start with a very large estimate and then gradually reduce the tolerance and adjust other parameters to get a more accurate solution. So I'm gonna leave it actually as, I'm gonna start with 1 degree. So GMAT will consider that the inclination has been achieved if we get to a value of 0 plus or minus 1 degree. I'm going to click apply and OK. And similarly, we want to describe the eccentricity of the orbit. So I'm going to rename this to achieve eccentricity. And remember, we want to ensure that our final orbit is going to be a circular orbit. So I can say that we have a 0 degree eccentricity of 0, and we can give that a tolerance of, for now, we'll call it 0.1 for now. We'll click apply and OK. So now we have configured this feature and this function for our target. And what we'll do is GMAT will continuously run through different values and try and find a solution. And once it does find a solution, then it will bring us through to our final orbit where we'll propagate that orbit for 1 complete day. So let's have a look at what we get. Let's save the mission and click run. So it says solve a subsystem exception, error inverting the differential corrector. It appears that the variables in the vary command do not affect the target parameters in the achieve command. Okay, so let's take a look at that. So variables in the achieve command. So here we forgot to set the eccentricity. So what we're going to do is going to go back to goal and change the eccentricity. Click OK and then apply. Now we're going to save and try running again. And here we go. So it said that we've converged upon a solution. And you can see that it's quite close in terms of the values that we got, but in terms of our analytical solution. So we've got minus 1.84, and our analytical solution is minus 1.83, and our y component was minus 3.923, and this is minus 3.91. And you can see that our desired inclination was 0, and they ended up achieving 0.01, which is very good. And you can see that it's not exactly 0, but it's very close to it. And you can see that our eccentricity achieved was very close to 0 as well, but not quite, not exactly 0. What I'm going to do now is actually, I'm going to deliberately increase the number of iterations and show you what happens when, and show you kind of how GMAT works to solve these problems. So I'm going to actually change the default orbit view, and we're going to set the view up condition as the X, and I'm going to move this over to the Z direction. So we can see a top-down view, and you can actually see GMAT work through different potential orbits. Okay, so in order to visualize kind of what's actually going on here, what I'm going to do is I'm going to minimize this, and I'm going to add a propagate here just so you can see GMAT working through the different solutions. So I'm going to set this color to maybe orange so you can see what's actually happening. Click apply and OK, and try run through this. So you can see back then, if I ran through it, hopefully, yeah. So you can see GMAT trying to find the orbit with that orange propagate. Now I'm going to deliberately set this to set these parameters something less achievable, and change the number of iterations to 200. I'm going to save this and run it now. And you can kind of see GMAT trying loads of different potential orbits and delta V's in order to find the solution. And obviously here, the closest it could get was 0.11. But we still converge upon a very close solution, but not quite within the constraints that we set. So this is why it's called a batch execution model. We can apply different levels of tolerance and see if we can converge upon the solution that we want. But it's best to start with a broader solution and broader constraints, and then work your way down from there. So here you can see again that we didn't converge. And now if I set it as a tolerance of 1 degree and click apply and OK, we should get our solution back, and we should converge upon it again. And you can see that we actually end up achieving a closer to desired value then by setting the tolerance to something that's less achievable. Okay, so that concludes this video and this tutorial. Hopefully you guys were able to follow along and perform the same. And hopefully you got an idea of kind of this batch execution procedure that takes place when using GMAT. So thanks for joining us today, and if you found this tutorial helpful, don't forget to like and subscribe to our channel for more space related content. If you have any questions or need further assistance, leave a comment below and we'll try and get back to you. Don't forget to visit our website HiveSpace UK for exciting space projects and applying this knowledge to real world problems. Thanks for watching, and let's do space right together. Thank you.